Hello friends, welcome to lecture series on essential mathematics for machine learning. Now in this lecture we will see that how we can find joint probability distribution and using this how we can find covariance. So let us start. Now we are having random vectors. What random vectors are? So let x1, x2 up to xn be n random variables. So these are n random variables. Then a vector x which is simply x1, x2 up to xn, this transpose, this is basically called random vector. That means if the collection of all the n random variables, that is called random vector. Now joint probability distribution. Now consider random vector x which is x1, x2 up to xn whole transpose. The distribution of this x, this random vector x, is called joint distribution of the random variables x1, x2 up to xn, defined as f x of x1, x2 up to xn. This means that probability when capital X1 is taking x1 value, capital X2 is taking x2 value and capital Xn is taking xn value. So, this is basically called joint distribution of random variables x1, x2 up to xn. Of course, for discrete case, if random variables are discrete, then this fx is simply we call it joint probability mass function, joint PMF. Okay. While for continuous case, if x1, x2 up to xn are these are continuous variables, continuous random variables, then this fx is called joint probability density function. Okay. So, basically till now we have seen that what is probability mass function or probability density function for a single random vector x. But now instead of single random x, we are having n number of random variables. So, now instead of finding for a single random variable, we are finding for a random vector. So, now instead of calling it a PMF or PDF, we are calling it joint PMF or joint PDF. This is the only difference. So, let us try to understand the concept of joint PMF or PDF using few examples. So, consider this example for joint PMF, joint probability mass function. So, what the example is? Now, consider an urn containing 6 red balls, 5 blue balls and 3 green balls. So, what we are having? We are having how many red balls? So, red balls are 6. Okay. Then we are having blue balls 5 blue balls, and then we are having green balls are 3 as per the question. Now, 4 balls are drawn at random from the box. The box containing total how many balls? It is 5 plus 6 plus 5, 11, 11 plus 3, 14 balls. Total 14 balls, we are taking out any 4 balls. Now, let x be the random variable denoting the number of red balls drawn and y be the random variable denoting the number of blue balls drawn. Then we have to find out probability mass function of capital X and capital Y and also the joint probability mass function of x y. So, how can we find? Let us discuss. So, x is a random variable denoting red balls. So, x may take values 0, 1, 2, 3 or 4 because we are taking out 4 balls from this box. So, that means this random variable x can take values 0, 1, 2, 3, 4. So, this is red balls are 6. What will be the Px of this? If we are taking out 0 balls means 0 red balls. So, from 6 red balls we are taking 0 balls and remaining are how many balls? 8. From 8 we are taking out 4. So, that means we are taking 4 balls. Now, from this for one red ball, so from 6 red balls we are taking out 1 and from 8 red balls we are from 8 total balls, total means blue plus green, we are taking out 3 balls. For this 2 it is 6 C2 and it is 8 C2. Then for x equal to 3 means we are taking 3 red balls, 3 red balls out of 6 balls. So, this will be 6C, that means we are taking out 3 red balls, 3, and it is 8C1 and it is 6C4, 8C0. And since it is a probability, so it must be divided by the total cases. Total are 14 balls and out of which we are taking out 4 balls. So, it must be divided by 14C4, it must be divided by 14C4, 14C4 and 14C4. So, this will be the probability mass function for x, random variable x, where x is the random variable denoting red balls. Okay. That means, if x equal to 1, suppose x equal to 1 means we are taking 1 red ball. If we are taking 1 red ball out of 6 balls, the total cases will be 6C1, and from the 8 remaining balls we are taking out 3 balls. So, it is 8C3 and divided by the total is 14C4. So, this will be the probability for x equal to 1, and similarly other cases we have discussed. Now, y denote the random variable denoting the number of blue balls drawn. So, now it is blue ball, y it is random variable denoting the blue balls. So, again how many blue balls we are having? 5 blue balls we are having. So, yes, we can draw up to 4. So, it is 0, 1, 2, 3, 4. So, what will be Py? Now, out of 5 blue balls we are drawing no blue ball, 0, that means 5C0 multiplied by remaining balls are 9, 6 plus 3 9. So, that means 9C4 upon 14C4. Here it is 5C1 into 9C3 upon 14C4 by a similar concept. 5C2, that means out of 5 blue balls we are drawing 2 blue balls and the remaining are 9 balls out of which we are drawing 2 balls. So, that means 14C4. Now, it is 5C3, 9C1, 14C4. It is 5C4, 9C0, 14C4. So, this will be the probability mass function for random variable denoting the blue balls drawn. So, in this way we can find out the probability mass function for capital X and capital Y. Now, suppose in the same problem we want to find out the joint probability mass function for x y. So, how can we find that? So, let us now we can see. So, red balls are, let us write it again. So, red balls are how many? Red balls are 6, 5, 3, then blue balls are 5, and green balls are 3. Now, we want to compute the joint PMF of x y. So, joint PMF of x y, let us denote it by f x y. So, now it can be calculated as. So, we want to find out, we want to take out x red balls and y green balls. Okay. We want to take out x red balls and y green balls. We can denote it by p also, as we have shown it here. As we have shown it here p. So, we can denote it by p also. Let us use the same notations which we have seen here. So, this will be, now x are the number of red balls. So, red balls means it is 6cx. Okay. So, let us see y are the number of blue balls. So, blue balls are 5. So, it is 5cy. So, we have taken out x plus y balls, but we need 4 balls. So, from the remaining 3 balls we can find out this much balls. So, that a total number of balls collected are 4 and total probability will be 14c. Now, of course, x plus y must be less than or equal to 4 and must be greater than or equal to 2, because see this value the maximum value this can take is 3. So, that means 4 minus x plus y should be less than equal to 3. So, that means x plus y should be greater than equal to 1. So, it must be greater than equal to 1 of course. So, it must be greater than equal to 1 and it must be less than equal to 4. So, this is the basically joint distribution function, joint PMF of x and y. Now, suppose from using this, if you want to compute the independent distributions of x or y, or we call it marginal distributions. Okay. So, let us discuss what marginal distributions are. Consider random bivariate vector x y and let f x y be the joint probability distribution of x y. The distribution of x is called marginal distribution of random variable x, defined as. So, here we can define basically if x and y are discrete, then the summing over y of f x y, this will give marginal distribution of x, random variable x. This we are finding from the joint distribution. This f x y is nothing but the joint distribution of x y, and if x y is continuous, so this will be simply integral over y of f x y dy. So, similarly the marginal distribution of y can be defined. Okay. So, let us try to understand the marginal distribution of x and y, how we can compute using this simple problem. So, consider a joint PDF of a bivariate random variable x y defined as this, f x y equal to this. So, here f x y is what? F x y is 6 x y square and 0 otherwise. So, of course, if you integrate it from minus into plus infinity and minus into plus infinity of f x y dx dy, it must come out to be 1. So, let us check. X is varying from 0 to 1, y is varying from 0 to 1. It is 6 x y square dy dx, which is equal to integral 0 to 1. So, these are the limits for y, these are limits for x. So, it is 6 x y cube upon 3, it is 0 to 1 dx. So, this will be equal to, this cancels from 2 times. So, this is integral 0 to 1 2 x dx, which is simply 2 x square upon 2 0 to 1, which is 1. So, yes, it has come out to be 1, and of course, it is greater than equal to 0 for every x and y. f x y is always greater than 0 for every x and y. The same properties which is for PMF or PDF for single, I mean for x or y, the same will also hold for joint distribution as well. That means the total integral should be 1, and for any x and any y, this f x y should be greater than equal to 0. So, this is joint distribution of x and y. Now, we want to compute the marginal distribution of x and y. So, let us compute the marginal distribution of x first. So, marginal distribution of x will be so we integrate this f x y over dy, and y is varying from 0 to 1 because it is a continuous function. So, this is equal to, this is 0 to 1, this is 6 x y square dx dy. So, this is 6 x y cube upon 3 from 0 to 1, and this is 6 x into 1 by 3, which is 2 x. So, this is the marginal distribution of x for this PDF. Now, if you want to compute marginal distribution of y, so marginal distribution of y will be integral f x y, not dx, x is varying from 0 to 1. So, this is equal to 0 to 1 6 x y square dx. So, this is 6 x square upon 2 0 to 1 y square. So, this is nothing but 3 y square. So, this is how we can compute marginal distributions of x and y if joint distribution is given to us. Now, how can you find covariance? So, what do you mean by covariance first? Let us discuss. Covariance is a measure of linear relationship between two random variables. If we have two random variables, then it give a linear relationship between them, and mathematically it is defined as like this, that it is simply expectation of x minus Ex into y minus Ey. Now what it comes out to be, it finally comes out to be this expression. Let us see how. So, what is covariance of x and y? Covariance of x and y mathematically is expectation of x minus x bar into y minus y bar. Here x bar is basically E of x and y bar is basically E of y. Now, if you simplify this, then it is nothing but E of x y, E x y minus y bar into x minus x bar into y minus minus plus x bar y bar. This is equal to E of x y. Now, by the linearity property of expectation, we know that this is E of x y minus. Now, y bar is a fixed quantity. So, it can be taken out. So, it is taken out, expectation of x minus, again x bar is a fixed quantity. For this random variable x, the mean is fixed. So, it can be taken out and it is expectation of y plus. Now, x bar y bar is totally a fixed quantity and again can be taken out, it is expectation of 1. So, this is expectation of x y minus. Now, E of x is basically expectation of x is x bar. So, it is x bar y bar minus again y bar x bar plus x bar y bar. Expectation of 1 is 1 itself. So, this is expectation of x y minus. So, 1 terms cancel out. So, it is x bar y bar and this is expectation of x y minus x bar is E x into y bar is E y. So, in this way we can find out covariance of x or y. Now, of course, if x y equal to x, if y equal to x, then this is nothing but these two values are same. So, it is simply whole square and which is nothing but variance of x. So, covariance with itself is nothing but variance of x. Next is covariance satisfy these two properties. What are the properties? That covariance of A x plus B y with z is nothing but A times covariance of x z plus B times covariance of y z. So, it is again very easy to obtain. I will try for the first one, the second one can be similarly obtained. So, let us try for the first one, covariance of A x plus B y comma z. So, this will be expectation of A x plus B y minus A x bar minus B y bar times z minus z bar as per the definition of covariance of x and y. Now, here x bar is nothing but expectation of x and y bar is nothing but expectation of y. And z bar is nothing but expectation of z. Okay. So, it is further equal to expectation of A x minus x bar plus B times y minus y bar whole multiplied by z minus z bar. So, this is equal to expectations of A x minus x bar into z minus z bar, okay, this into this plus B times y minus y bar into z minus z bar. So, this is equal to, now by the linearity property of expectation we know that this is equal to A times expectation of x minus x bar into z minus z bar plus B times expectation of y minus y bar into z minus z bar. So, this is A times covariance of x and z and plus B times covariance of y and z. So, other property can also be easily obtained. Now, suppose you want to find out the joint the covariance of the random variables x and y whose joint PDF is given as this. So, how can we find? So, now let us see. So, what is joint PDF here? Fxy is 2 when x is greater than 0, y is greater than 0 and x plus y is less than 1 and 0 otherwise. So, again one can easily check that it is a PDF by integrating double integral of this in this range. This is equal to 1 and of course, f x y is greater than or equal to 0 for all x and y, that is obvious. Now, if you want to find out covariance of x and y for this particular problem, so this is as per the definition, this is expectation of x y minus expectation of x into expectation of y. So, first of all we have to compute expectation of x and x into y. So, expectation of x y is equal to double integral from, I can take it minus plus infinity, then this is fxy xy into fxy dx dy. I want to compute the expectation of xy. So, for that I need joint PDF. So, joint PDF is fxy. Now, this is equal to, now it is 2 in this range, otherwise it is 0. So, what is this range? This is x plus y less than 1, this is x plus y equal to 1 and x plus y, x and y greater than or equal to 0 means this area. So, if we take it x y and f is 2, suppose we take it dx dy. So, we take a strip parallel to x axis. So, if you take a strip parallel to x axis, what is x here? X here is 0 and what is x here? X here is 1 minus y, okay, and y is varying from 0 to 1. So, this is 2 times integral y from 0 to 1. Now, you have to integrate x here. X is what? X square upon 2, 0 to 1 minus y and it is, okay, you have to integrate with respect to x. X means x square upon 2 and this is y dy. So, this is 2 cancels out and this is integral 0 to 1, this is 1 minus y whole square into y dy. This is integral 0 to 1, this is 1 minus 1 plus y square minus 2y times y dy. Now, when you integrate it from this you will get y means 1 by 2, this is y cube that is 1 by 4 and this is 2y square that means minus 2 upon y cube that is 3. So, you can take LCM that is 12, that is 6 plus 3 minus this is 4 into 2 is 8 and that means 1 upon 12. So, this is 1 upon 12. Okay. Now, but to compute expectation of x or expectation of y, first we need marginal distributions of marginal PDF of x and y. So, first is marginal distribution of x. So, marginal distribution of x will be it is integral over y and it is integral over y to, so y is varying from where to where? See, in this example y is varying from 0 to 1 minus x, okay. So, that means y is varying from 0 to 1 minus x and it is basically dy, okay. So, this is equal to 2 1 minus x. Similarly, marginal distribution of y will be integral x is varying from 0 to 1 minus y 2 dx. So, it is 2 1 minus y. So, expectation of x will be integral x into f x x dx and x is varying from 0 to 1. Okay. So, this is integral 0 to 1 x into 2 x into 1 minus x dx. So, this will be equal to 2, it is x, x means 1 by 2 minus 1 upon 3, that is 1 by 3. Okay. And similarly, expectation of y will be again 1 by 3 because it is symmetrical with respect to x and y. Okay. So, what will be covariance of x and y now? So, covariance of x y will be equal to expectation of x y 1 upon 12 we have just computed into 1 upon 3 minus 1 upon 3 into 1 upon 3. So, that will be the expectation of x and y. So, that we can calculate 1 upon 3 can be taken out common. So, it is this value, this is 1 upon 3 into minus 1 upon 12, that is minus 1 upon 36. So, that will be the covariance of x and y. So, in this case they are negatively correlated. That means if x is increasing, y is decreasing, or y is increasing, then x is decreasing. Okay. So, in this way we can find out covariance of two random variables x and y. Now, the correlation coefficient of x and y may be defined as covariance of x y divided by standard deviation of x into standard deviation of y. So, this is basically a coefficient, and if it is 0, two random variables are said to be uncorrelated if covariance is 0 or correlation coefficient is 0. Now, if two random variables are independent, then covariance between them is 0, or we can say that correlation coefficient is 0, but converse is not true. See, this is an example which we can easily see. In this example, if we take y as x square, a random variable y is taken as x square. So, clearly they are not independent, they are dependent, but still if you find the correlation coefficient or covariance of x and y for this particular problem, then it comes out to be 0, or we can say that they are uncorrelated. If you find covariance of x and y, which is expectation of x y, which is by this definition, it is expectation of x y minus expectation of x into expectation of y. Now, y is x square. So, it is expectation of x cube minus expectation of x into expectation of x square. Now, what is expectation of x cube for this problem? For this problem, expectation of x cube will be integral minus 1 to plus 1 by 2 x cube dx. Okay. But x cube is an odd function, so it is directly 0. And similarly, expectation of x is again 0, because that is nothing but integral minus 1 to plus 1 x into f x dx, which is again an odd function. So, since both the terms of this expression, this is 0 and this is 0, so we can say that covariance of x and y is 0. So, they are uncorrelated, but still they are dependent. So, we can say that if they are independent, then correlation coefficient is 0, but converse may not be true. Now, if we have a random vector, then we may have expectation of this random vector, and that can be defined as expectation of x in x1, expectation of x2 into up to expectation of xn. And in this case, if we are having a random vector, in this case we have covariance matrix, and the covariance matrix can be defined as, this is sigma, this is a notation for covariance matrix, and this may be defined as expectation of x minus Ex into x minus Ex transpose. So, that is given as when they are equal. So, this gives variance. When it is x1, it is x1, it gives variance. When it is x1, it is x2, it gives covariance of x1, x2. When it is x1, it is x3, covariance of x1, x3, and similarly others. So, instead of this, basically gives a covariance matrix. Okay. And we have a very important property of covariance, this covariance matrix, and that is, first of all, it is symmetric. That is clearly seen from the matrix itself, because this matrix is equal to its transpose, and number 2, this is always positive semi definite. So, why we are saying it positive semi definite, that is easy to prove. So, let us see. So, when a matrix is said to be positive semi definite, so a matrix M of order n cross n is positive semi definite if x transpose m x is greater than or equal to 0 for all x belongs to Rn. Now, we want to show that this summation matrix or the covariance matrix is positive semi definite. So, let us take a vector z, let z belongs to Rn and take z transpose sigma z, and we want to show that this is greater than or equal to 0 for every z. So, this is z transpose and this I is nothing but expectation of x minus expectation of x, or we can call it x bar. X bar is nothing but expectation of x into y minus y bar transpose into z. Okay. So, we can see it from here, it is expectation of x in minus E x, expectation of x minus E x. Okay, x minus E x again will come because it is a vector. So, this x is basically x 1, x 2, x 3 up to x n. So, this is further equal to, we can, because this z is vector free from x. So, we can take it inside. So, it is z transpose x minus x bar into x minus x bar whole transpose into z. We can write it like this, and this is equal to expectation of x. Okay, this is equal to expectation of, we can write it like this, z transpose x minus x bar into z transpose x minus x bar whole transpose. So, a vector multiplied by its transpose, that is nothing but norm square. This is nothing but multiplication of this into this. This is nothing but z transpose x minus x bar. Okay. Now, we know that if this is positive, then expectation is also positive. So, that is greater than or equal to 0, because this is always positive, this is norm square is always positive. So, expectation of a positive quantity is always greater than or equal to 0. So, we have shown that this is greater than or equal to 0, that means covariance matrix is always positive semi definite. So, in this way, suppose two random variables are given to you and you want to find out the covariance matrix for that. So, yes, we can find out. How we can find out? We have to first find the variance of x 1, variance of x 2, covariance of x 1 x 2, which is equal to of course covariance of x 2 x 1, and that 2 cross 2 matrix will be basically covariance of random variable x and x 1 and x 2. Okay. So, this examples can be solved very easily. If you want to find out covariance of covariance matrix of this two random variables x and y whose joint PMF is given as this, that can easily be obtained using this definition. So, in this lecture we have seen that joint probability distribution is given to you. How can you find out marginal distributions, and using that how can you find out covariance of random variables x or y. Not even two random variables, if you are having a random vector containing n random variables, that we can also find out the covariance matrix, which is having two important properties, that is first of all it is symmetric and second it is positive semi definite. So, these terms we use in machine learning, covariance, how we can find out covariance or how we can find out covariance matrix of a random vector. So, thank you very much.